A reminder of how we should look after our health, with A&Es everywhere feeling the strain, particularly at this time of year. There's no doubt that organ transplants save lives, but waiting lists for compatible donors can never be short enough. So what if there were a way of producing compatible organs on demand? Bioprinting has traditionally meant printing biocompatible materials as a base for cells to grow. Though it may sound far-fetched, scientists have already managed to print a human ear and other tissues. Doctors take a scan of the organ to create a 3D blueprint. Cells are then taken from the patient, which are then placed in a culture to multiply. The cells are then painstakingly placed on the 3D printed scaffold, which is then incubated to produce a functioning organ. 3D Bioprinting Solutions opened its labs in September 2013, with the sole purpose of advancing tissue engineering. Supported by the Moscow Department of Healthcare and in vitro labs, the Skolkovo resident should soon have all the equipment necessary to manufacture organs. It's also working on a revolutionary bioprinting technique. The method still requires the 3D printed cell molds commonly used to store and grow various cell types, but crucially, it no longer requires the scaffold around which they are placed.
In 2014, Russia will have its first 3D bioprinter. This will far surpass any previous models, as it will be produced using nanotechnologies. Its speed and accuracy will far exceed that of any of the current models. And perhaps most importantly, it won't even be that expensive.
Traditional tissue engineering methods involve removing all the cells from a dead human or animal organ, leaving only the protein scaffold, which is then repopulated with stem cells and incubated. Mironov has taken this a step further and has come up with a method for printing an organ directly without the use of any organic or artificial scaffolds. It involves extracting stem cells from the patient's fat tissue, which are then mixed with a hydrogel and placed in 3D printed molds. These are then incubated to produce spheroids, which are the building blocks of organ printing. From here, you can pretty much print any organ you like.
We do not use animals or any synthetic polymers for support structures or scaffolds. We only use hydrogel.
The hydrogel is 99% water. It contains the spheroids, which are each made up of tens of thousands of cells, together making the bioink used to create organs. The printer lays down a layer of biopaper onto which the cell clusters are printed. Cells of the same type are naturally attracted to each other and combine to produce tissue. The process continues in this way, layer by layer. The biopaper eventually dissolves and the layers fuse and self-organize to produce a fully functioning organ.
The simplest tissues are those that don't have blood vessels in them, such as cartilage, skin, bones, and so on. The organs that we really need are kidneys, livers, hearts, and lungs. But that may only be possible in the distant future.
Although printed organs might not be here quite yet, doctors can already do some pretty impressive stuff. Stem cell therapy involves using new adult stem cells to regenerate damaged or diseased tissue. It may still be in its infancy, but doctors believe that the treatment has the potential to treat anything from spinal injuries and cancer to baldness and missing teeth. Heart disease is one of the biggest killers there is, with heart valve transplants running into tens of thousands in Russia every year alone. Thankfully, Penza-based Miedinja's pyrolytic carbon heart valves are indistinguishable in terms of performance from the real thing, but provide the long life offered by artificial ones, giving many people a second chance. Bone implants are now commonplace, but that doesn't make them any less advanced. Porous nickel-titanium alloy is a promising new material that's flexible when cold, but snaps back into its original shape at body temperature. But, just like soft tissue organs, bone implants also need to be accepted by the body, so they're given a special coating.
The surface coating should have the exact same composition as bone, so that the body doesn't reject the implant once it's inserted. So our task is to minimize the difference between the bone tissue and the implant. Ultra-thin calcium phosphate films do this perfectly.
Calcium and phosphate together make hydroxyapatite, which is a natural component of bone. The coating is applied by a process called physical vapor deposition, where calcium and phosphate are vaporized into a plasma, then condensed into a thin film onto the implant in this patented vacuum chamber. The whole procedure takes several hours, but the finely tuned ratios ensure the long-term success of the implant. The atoms gradually dissolve, stimulating bone growth around the implant, which results in a solid, natural bond.
As well as modifying bone implants, we have started researching ways to make ultra-thin coatings for coronary stents. As we all know, any malfunction of the cardiovascular system could be lethal. That is why searching for new ways to prolong the life of the patients is of utmost importance.
Stents are small mesh tubes that can be expanded to keep weak or narrow arteries open. Unfortunately, delicate arteries can be damaged during the implant operation or subsequent expansion. So, to avoid complications after the operation, the stents are coated in titanium nitride oxide, or TiNO for short. The super smooth coating helps avoid arterial damage and promotes healing, significantly reducing the risk of blood clots forming or the artery collapsing again later. The coating also remains intact as the mesh tube is expanded within the artery. Just like bone implants, the stent coatings are applied using the PVD process.
There is so-called early thrombosis and late thrombosis. The stents currently on the market guarantee successful treatment for older patients with early thrombosis. But there's increased risks of late thrombosis occurring even after several years. Our preliminary findings allow us to predict that we can avoid both early and late thrombosis.
Given all the medical breakthroughs we've already made, and with 3D printed ones coming in the not too distant future, hopefully we'll be able to start worrying less about our health